All right, so as we're looking here at lesson 73, we want to look at some of the things that we've considered in relation to our natural logs and natural exponential functions, and deal with it when it's not the natural. It doesn't have a base of e. How do we handle those other bases? And at the root of all of this really is our change of base formula. Okay? Now, let's warm up a little bit here, just working with a couple of these, and see what we can do. All right? Now, we have the log base 2 of x that we want to find the derivative of. Okay? And you guys know from pre-calc and algebra 2 that you can rewrite the log base 2 of x as a log base 10 or a log base 5 or a log base whatever you feel like using our change of base formula. Okay? Now, the useful one for us is going to be the natural log, the log base e. So I'm going to rewrite this so that we are finding the derivative of ln of x over ln of 2. Okay? I've changed the base to e, and the reason for that, notice now I can see this as ln of x times 1 over ln of 2. And 1 over ln of 2 is just a constant, okay? So I know that this is going to be 1 over ln of 2 times whatever the derivative of ln of x is. And you guys already know that that is what? 1 over x. Okay, so now this is 1 over x times 1 over ln of 2, so we can rewrite that as 1 over x ln of 2. And there's our derivative of log base 2 of x. Okay? So it's not a huge change here, but it's just using some tools from the past to help us. Okay? Another thing that's helpful is just making sure we remember how to solve these, because chances are we're going to be setting derivatives equal to 0 and stuff like that again, right? So here, if I were solving for x, we would take a log with a base equal to the base of our exponential on both sides. So we have a log base 3 of 1/81st. Okay? Well, that log base 3 is the inverse of an exponential with base 3, so that leaves us with just x. And then you may recognize that 1 over 81 is 3 to what power? Yeah, it's 3 to the negative 4th power. Okay, it's a fraction, so we know it's negative. 3 to the 4th is 81, because 9 squared is 81. So that's 3 squared squared, or 3 to the 4th. So that means our solution here is simply x equals negative 4. Okay? So we've kind of been able to use some of the rules we've already learned to kind of get an idea of how we're going to handle derivatives when the log has a different base, but also we want to make sure we remember our different properties, okay? So let's rethink, by putting some different ideas together, let's rethink how we would define an exponential function that has a base of a, all right? Remember that e and ln are inverses of each other, so if I have e to the ln of x, that simply equals x, all right? So what I'm actually going to do is I'm going to rewrite this value of a as e to the ln of a, okay? E to the ln of a just equals a. And then that would be raised to the x power. Okay? So, that's going to be at the root of how we will take derivatives of exponentials in this case as well. We already looked at derivative of a log. So just remember our properties here. Anything to the 0 is 1, as long as it's not 0 to the 0. Okay? If I have a to the x over a to the y, I can subtract the exponents, a to the x minus y. If I'm multiplying, I can add the exponents. And if I'm raising a power to a power, I multiply those exponents. Okay? So now, here's kind of a blast from the past. We have half-life models. Okay? Half-life models. So, we think about this, okay? Let's think about our amount at time t. This says that the half-life of carbon-14 is about 5,730 years. If 1 gram of carbon-14 is present in a sample, how much will be present in 10,000 years? Okay, so remember our amount at time t is always given by our starting amount times 1 plus the rate of change to the t power. Okay? Now our rate of change, since we're dealing with half-life, is what? A half. Okay? Minus a half, right? Because it's decaying. So r is minus 0.5. Our a sub 0 is that starting amount. So 1, and it's 1 minus 0.5. You may have memorized some kind of a half-life formula in the past, but if you understand what you're doing, it's not too bad. Okay? Now, time. Our rate was a minus 50% per half-life. Okay? So our time needs to equal half-lives. We need to match the units, okay? So if we have 10,000 years and the half-life is 5,730 years per half-life,
we need to divide 10,000 by 5,700.
There we go. If I do 10,000 years divided by 5,730 years per half-life, my years will cancel, and if I flip that, I'll get half-lives as my unit of measure. Or half-lives. Half-lives. Okay? Half-lives. Alright, so 10,000 over 5,730. Okay, could probably reduce more, but I'll reduce it at least to 1,000 over 573. Okay? Notice that half is part of the unit of measure. It's not anything mathematical here. Okay? So, what's the time I plug into my formula? I plug in the 1,000 over 573. So now my units of measure match up. My rate was in half-lives, and this is in half-lives. And now we simply plug that in. A of 1,000 over 573, because that's my time here, is going to be this, okay? So what do we get when you plug that in? 0.298. Okay? And this would be in grams. Okay? So we're reviewing a few things here just to keep our minds going. But notice here, if I were writing this as an exponential function in terms of t, the base of my exponential would be 0.5, right? So if I were doing anything else with this, like finding a derivative, how fast is it decaying at that moment, okay? If I were doing a derivative of some sort, I'd have a function with a base of a half, and I'd have to use the strategies that we were looking at earlier, okay? Now, here is what we were looking at before with our change of base formula. The definition of a logarithmic function to base A. Basically, the change of base formula is another way of defining any logarithm with a base. You can define it all in terms of the natural log. So ln, the log base A of x is ln of x over ln of A. We don't need to go over these properties again, but notice the inverse properties, just reviewing from a couple of lessons ago. These apply not only in natural log situations, but anytime we have a log, as long as the bases are equal. Okay? I'm not going to go through each of those individually, but let's go ahead and do a little bit of practice solving some of these exponentials. Okay? You guys know how to do this, so take a minute or two here and try them. Alright, what'd you guys do with A?
Log 3 on both sides.
Okay, log base 3 on both sides. A 3 to the x over 2 equals log base 3 of 54. Okay.
And then it cancels on the left side.
Okay.
And then do log base 3 of 54 and multiply by 2. And that's like 7.26.
Okay. It's 7.26. Alright, so yeah, this log base 3 of 54. 54 is 27 times 2. So it's not a straight power of 3. So we can't really do this in our heads. What's that?
Could you do something else? I mean, it would be 3 to the third times 2 and then times another 2. Could you, like, put that into terms of x or no?
I mean, if you saw this as 27 times 2, I guess you could rewrite it as log base 3 of 27 times 2, since it's multiplication. Log base 3 of 27 plus the log base 3 of 2, and this would equal 3. However, you'd still have that other part you'd have to get with the calculator, so it's not bad thinking, but it just, we eventually would have to use the calculator anyway in this case. So you said x is 7.262. 262. Okay, good. 3 decimals for AP. All right. And then the part B. Make 2 the base of an exponential. So it's 2 to the log base 2 equals 2 to the negative 4th. X is 2 to the negative 4th, 1/16. Okay? So again, that's not too bad a one. Pretty easy. A little bit of review. Okay. 3x. Whoa. Alright, so that brings us to our last part here, which is derivatives for bases other than e. Now these rules here can all be derived based on the things that we just saw earlier. Okay? Using the different rules, we can convert a to the x into, remember, ln of, or I'm sorry, e to the ln of a times x, right? Because e to the ln of a equals a. So when I do that, then I multiply the exponents. It's ln of a times x. But now the reason why that's useful is because now I'm taking the derivative of e to the u. And the derivative of e to the u is e to the u times the derivative of u. Well, the u is ln of a times x. That's a linear. So the derivative is just the slope of that linear part, and that is ln of a. Okay? Well, now we go ahead and we simplify this part back to where we started, and we have ln of a times a to the x. All right, and that's how we would get this rule right here, the first rule. We would use a similar process if it were a to the u instead of a to the x. Yeah, Ryan?
Is that a just a constant?
Yeah, it's some base. Like we have 3 to the x and we want to take the derivative of that, or 5 to the x, just like we're dealing with e to the x. Okay, so a is just some other constant. All right? Now for our log, remember we can rewrite the log base a of x as, well, let's see, how would we want to write that? We can rewrite that as ln of x over ln of a, and this is what we were looking at on the very first example today. Okay? That's a constant, 1 over ln of a, times the derivative of ln of x. Okay? Well, the derivative of ln of x is 1 over x. So we get 1 over ln of a times 1 over x, and that's how we get our solution here, 1 over ln of a times x. Okay? So those are our basic derivative rules, and of course the u's just throw in a chain rule. It's the same rule, just times the derivative of u. Okay? So, looking down here, if I have y equals 2 to the x, if I want dy dx, or y prime, looking up at our property, we have ln of a, so a is 2, so it's going to be ln of 2 times a to the x, so times 2 to the x. Okay? If I have 2 to the 3x, dy dx is going to equal ln of 2 times 2 to the 3x times the derivative of 3x, so times 3. Okay? Now, there's all kinds of stuff that you can do to simplify this, depending on how far you want to go. We could make this into a 3 ln 2 times 2 to the 3x. We could pull the 3 in and make that an ln of 8 times 2 to the 3x. If we really, really wanted to, we could pull the 2 to the third and the 2 to the x apart. Ln of 8 times 2 to the third times, oh wait, no, that would be 2 to the third to the x. So that we couldn't really simplify anymore. I got a little carried away there. Alright? So we could do that if we felt like it, but you don't necessarily have to. Okay?
Wait, so how do we get ln of 8?
ln of 8, I took that 3 from my chain rule. The 3 from my chain rule. And because I have a log times a constant, I can pull that in as an exponent. 2 to the third would be an ln of 8. Like I said, you don't have to do that, but you can. Now, notice the similarity here. We had before the derivative of e to the x is e to the x. Now it's just the derivative of a to the x is a to the x, but then you got to multiply by ln of a. Okay? All right, our last part here, log base 10 of cosine of x. I'm going to rewrite y as the natural log of cosine x over the natural log of 10. And then what's the derivative of ln of cosine of x? 1 over cosine x times the derivative of cosine, which was negative sine x. Good. Okay, so we've got that.
How come we wouldn't do the formula of that's log a to the x equals 1 over ln a times x?
We have 1L. This time we have a u. The u is the cosine x, right? Okay, so just using that formula up here that you're saying, okay, it would be 1 over ln of a. Okay, ln of a is ln of 10 times the u. The u was the cosine x. Okay, times du dx. The u is cosine, so du dx is a negative sine x. Whether you use the formula or you actually rederive it, it may even just be easier to rederive it, because the derivative of ln of u is u prime over u. Well, that's a negative sine x over cosine, right? And then it's times a 1 over ln of 10. Either way, you're getting the same place. Negative sine over cosine ends up being a negative tangent. So I have a negative tangent x over ln of 10.
I have a question.
Yeah.
What's a hypersine?
Hyperbolic sine?
Yeah.
Hyperbolic cosine? Honestly, I used that once a long, long time ago in college for like something, and I don't even remember.
Because it was on one of the answers for the review. I don't know. I just like looked it up.
I'd have to look at that.
Okay.